Hello, welcome back to another lecture in low-level programming stroke writing an operating system. Okay, I'm going to carry on today with where we left off really. So in the last lecture we looked at the stack, which is basically a convenience so that we can store things in memory without really worrying where they are, just for temporary data. We're going to touch on the stack again today because it relates to this stuff. And we also looked at flow control, so the idea that like how to do branching, jumping, if, else, loops and things like that in assembly. And we're going to be using a bit of that today as well. So today I'm going to talk about functions. Now if we've written stuff in Java or Python or C or whatever language, then we kind of take a function for granted, and then we have this idea where we can define a function and it's got some arguments, might have no arguments, and then we just, somewhere else in our code we can call that function. So the purpose of a function really is just for reuse of code. If we find that we're doing two similar bits of work and we can share the same code between them, then it makes our code easy to manage. It means that we can, well, firstly we can encapsulate specialized code within a function, and the rest of the code that calls that function doesn't need to worry too much about how that function works internally. We see this with object-oriented programming at another level of abstraction above that. But so yeah, we've got this idea of a function. So functions are very useful because we can break down our code, and yeah, we don't want to be writing loads of code again, especially if it's in assembly as well. And usually in assembly, well, I find anyway, and probably most people, because it's not so widely used now, you find that you forget certain instructions, or you forget certain operations, or certain tricks to do certain algorithms that you've done in assembly. And if you can write them once and keep them somewhere in like a library almost, then you can reuse them. Anyway, functions are good. So what does a function do? It takes some arguments and it usually returns something. But what we're going to see is that the computer doesn't really know about functions. All the computer does is execute sequences of code, and now and then it jumps from one place to another place in memory and carries on executing that code. As far as the computer is concerned, when you call a function, it just jumps to a piece of code, and if you call the function twice, it's just going to go back to that piece of code later on and then jump back from it. So we're going to play around with a function. We're going to look at how we can create a function, and remember, a function is just an abstraction to make it easier for us to think about how we structure our code. And then we're going to write a print function that prints a string. So far we've printed characters, single characters, but we'll write something that prints a string using the looping stuff we looked at last time, and using that BIOS function to print a character. Yeah, okay, let's get on, let's have a look at some code. So like always, I'm going to start with something that should be familiar now. So we're just, I'm going to build this example up again like I did before. But we've got, what have we got here? This is just my boot sector, and it just prints an X, and it's just based on the stuff I talked about in the last lecture. I set up the stack here. So the reason I set up my stack by setting these special stack registers is just that I want to make sure that it's clear of my code, because when you're pushing things onto the stack you don't want to overwrite your code, and I don't know where the stack was set up when BIOS loaded, so if I set it myself at least I know where it is. So I'm going to set it up at 8000 hex. So the other thing I do is I just print an X using the same BIOS thing that I used before. So I load OE into the high 8 bits of the AX register, the ASCII value for the character X into the lower 8 bits, and then I call interrupt 10 hexadecimal, which causes BIOS to print it. So let me just run my code, because it's always good before I start adding stuff to it. It's good to make sure that it's working. Yes, so it's printing X. So just to remind you, I'm working in an emulator here, which is emulating a real x86 PC. So the code that we're running here is assembly code, but it's running at the lowest level of the computer. Right, let's get on. So what I want to do, well, how would I make a function? Well, let's start with, supposing I've got this code here. Supposing this piece of code down here, I want to make it reusable, so that I can print a character when I call it in different places. So what am I doing here? There's three things I do. I move the character into the AL register, I move the BIOS teletype sort of number there into the higher AX register, and then I call interrupt 10. Well, the first thing we need when we're making a function, because a function is just a piece of code that we call over and over again, we need a way to reference the start of that code, so we just use a label. So I'm going to call it print char. Okay, now just to make it easy for me to see this code, I'm going to indent this assembly. Sometimes you see people indenting their assembly line, sometimes you don't. The truth is, it doesn't really matter, because there's no real blocks of code. We just have labels that define areas of code. And like we saw when we looked at the conditions, do you remember there was that little thing where it's very easy when you have an if-else statement, if you don't have a jump at the end of the first block, out of there to the end of the if-else statement, then you end up running into the next block, because there's no concept of blocks. We just have to jump in and out of code. Okay, but anyway, let me just indent this just so that I can see that what I mean by this. So what have I got here? Well, I've got this function print char. It's not really a function yet. All I've got is a label, so I know that when I want to print a character, I can go to that label, and I know how to do a jump in assembly because I can type jump print char, and that will jump to the address print char, which is just below it. So what I'm going to do is, the other thing is that if I run this boot sector code now, well, we'll see what will happen. We can run it. It prints an X. Now, the reason it printed that X was because when the CPU started executing my instructions, it did this, it did this, it did this, it came down here, did this and this and this, and then it went to the jump. Now, I don't want my function to run just because I've declared it there, so I'm going to move my functions below my jump statement so they won't execute directly, so that if I want to execute that code, I'm going to have to jump to it. So let me just write here functions, so I can put my functions underneath here. And I want to print a character. Well, let's use the AL register as our argument. We're just playing around with some ideas here to understand what functions are. So now what I do is I move, first of all, let me get rid of that jump. Just comment that out. So obviously this isn't going to do anything now, because there's no print, there's no call to BIOS to print anything. But when I put this in, it should jump now to print char and execute this code. So let's try that. Okay, that's good. Now, let's say I want to print a Y as well using my same function. So I want to print an X and then a Y. So what does this code look like? Well, it's going to call, it's going to set X into the AL register ready for the BIOS stuff that happens here. It's going to jump to print, and then later on it's going to move a Y and it's going to jump to print char. Okay, let's see what happens. So hopefully it should print an X and a Y. Oh, it just printed an X. Okay, why has it done that then? If we look back at the code, the problem here is, well, the whole idea of a function is that you call the function and then a function returns, and then you carry on from the next line of code before you call the function. I mean, after you've called the function. So what we want to do is come back to this line of code after we've finished printing the function. But how do we get back to this code? Well, we have to jump to it. And how do we know where it is? Well, we have to set a label, because there's no other way of knowing where to jump back to. So to make this work, what we'd have to do is put a label here. So let's call it return to. Okay, so this label now, I should be able to, when I've called my function, I should be able to jump back from the function to that label. Okay, so what this should do now is I move x into AL, I call print jar, so I'm using AL as the parameter for this function. One thing that we need with functions is a convention between the person calling the function, or the code calling the function, and the function. It needs to know, because there's no magic, there's no idea of functions in the computer, there's no magic, so when that function code executes, it needs to know where to get its parameters from. And we'll see that there are different conventions, and when we look at C later on, we'll see how C does that using the stack. But we can pass things by any means we want to, as long as the function that we're calling knows how to access those parameters that we passed. So in this case we're just using AL, and that's convenient because that's the AL is what we set up the character for when we're printing BIOS. Okay, so what does this do? So it prints an X, it jumps the print jar, it should print out what's in AL, and then it should hit this jump, and it should come back to return to, and then it should move Y into there, and then jump back to print jar. So let's see what happens now. And then it should finish on this loop. Okay, what's gone wrong there? Let's have a look. So it printed lots of Y's. Actually it printed the X and then it just carried on printing Y's. So the problem is now that when we reach the end of this function, it's going to jump back to return to, and it's going to go here, and it's going to call print jar, and then it's going to jump back to return to. So this is a loop I've got here. So the problem is that really I don't want to return to the same address. I want to return to the address after the function was called, just after it was called. Okay, so we need something to help us here. Now we have got instructions to help us, and that's what I'm going to show you now. Just to understand that, I said the CPU had some special registers. Well, it's got lots of registers. Well, not loads and loads and loads. You could learn what they all are, but it has special purpose ones. And this is a register called the IP, the instruction pointer, that points to the next instruction in the CPU that's going to be executed. And this, by using this, it should be possible before we call the function to store that address of the next instruction, call that function, and then return to it. And we'll see that one way we could do that is to store it on the stack. We could push the return address onto the stack, call the function, and when the function returns, pop the return address off the stack and jump back to it. And that's what we need to do. Now, one thing, we can't directly read the instruction pointer register. We can't just access it. We can't just say move AX IP like this, for example. So if I'm going to call jump print jar here, I might want to, somehow find the instruction after. Let's get rid of this return to now. I'm going to get rid of this idea because it doesn't work. So when I call jump to print jar, I want to make sure that I can return to this address. Now, if I could do something like this, move BX IP, and yeah, something like, you're going to see you can't really do it like this, but you can imagine that I could store the current instruction pointer and work out which the next one would be after this one, store that on the stack, push it onto it, jump to that print jar, and then when I return I could pop that address off the stack and jump back to it. Anyway, this is what we're going to do, but there's a function that does exactly this. And the reason I'm explaining how it works is because I want you to understand that it's still just essentially a jump, what we're doing here, but it's just that we're storing the address that we're jumping from so that we can jump back to it, or to the instruction after it. So if I call this instead, if I do call, then what this does is it, and I'll do the same here, when I call print jar, it's going to jump to that label, but it's going to store the instruction pointer of the next instruction, which is this one on the stack. And let me just see if I can demonstrate that. Well, first of all, let me just run this and see what happens now. So I've got call in there now. So do we print an X and a Y? We just print an X, okay. Now the reason why we just print an X is because we need to use that value that's pushed onto the stack to jump back. Now if I look at my stack, let's see if I can do this manually. So I set my stack up at this address, 8000, and when I call, the CPU pushes, remember I was talking about the stack, well the CPU uses the stack for things as well, so when I do this call, the CPU automatically pushes an address onto the stack for me. I don't need to push it on. Now let's just see what happens if I can get the address off the stack. So if I do pop, let's stick it in, I don't know, DX, can we stick it in there? Pop DX. Now this should pop the return address off the stack that call pushed on, and let's try that, see if it works. Just playing around with ideas now. So we've got an X and a Y, excellent. And that's quite nice because we demonstrated that that call was using the stack, so the CPU was using the stack on our behalf to store that address on. Now just to double check that, if I put another one in here, just to check that it's all working, to check that we're not jumping back to the same address, but we're jumping back to the address after the call was made. Let's try that. Print XYZ, that's good. So, well that's good then, so that's how it works. So call is what we use for creating functions, because it allows us to, it stores a point for us to jump back to, and that's the role of call. Now when I did pop dx, jump dx, actually there's a command that does this, called ret for return, and if I run this code now it should do exactly the same. Yeah, it's printing X, Y, Z. So this is what I use to create a function. So I have a call and I have a ret to come back from it, and underneath the surface that's using a stack. Yeah, so this is all the CPU really gives us for creating functions, call and return. But that's how the compiler, when it creates functions in C, that's how it does it. I'll look at C later on, but there are different ways of, sometimes it doesn't create a function at all. When you're having line functions and stuff, it tries to optimize it so that it doesn't actually, it might not even have a jump to the code. Anyway, so we've got call and return, so now we can start to build a function. So yes, passing arguments. Now we used AL to pass the argument here. It doesn't really matter how you do it. You can pass it through registers. We could pass it through the stack. I'll probably look more at that when we look at C, but I could, as long as I know, as long as the function, so for example, I'll just, this code won't work because we need to it's probably more confusing to do it like this, but for example if I did push X on here, and then what I could do is pop AX here. Remember that the stack pushes, when you push something onto the stack, it pushes on 16 bits a word. If you're doing it in 32-bit mode, which we'll do later on, it will push 32 bits on. So although I push a single byte, a character there, it's going to push 16 bits on 2 bytes. So what I'm doing here, I just, in my function, I reciprocate what I do when I call the function. So here I push an X onto the stack, and here I pop off whatever was on the top of the stack, which should be my X, because that's what I pushed on just before I called this. It pops it off, and then that should that should then move into the high bit of AX register. It should move the BIOS teletype printing, and it should print it. Let's just see if that works now. There's a little thing that we're forgetting. It didn't print it. I told you it was probably more confusing to do it this way. But what happened is, if you remember, I push an X onto the stack, yeah, and I'm expecting here that my X is on the top of the stack when I pop it. But what actually happens is, I push the X on the stack and call. When this call happens, this pushes the return address onto the stack. So actually, when this function is called, the top of the stack is the return address. If I did pop AX again, the next one, so this should store the return address into X, and this one should store the character that I pushed on into AX. Because my character wasn't at the top of the stack when the function was called, that was the return address. Let's see what happens now. It prints my X. The thing is here though that I called return here, and because I popped the return address off the stack inside my function, it means that that return is not going to work. It's possible it might be if it stays on the stack, if it stays in the memory and nobody else uses a stack in between, but it's not guaranteed. So anyway, let's just forget about that. But the idea is that I can pass the way that you pass arguments to a function. It doesn't matter how you do it. You could pass it. I could store the value in some specific memory address before I call the function, and then the function can reference that specific address to use the argument, and that would be equivalent of using a global variable in C. As long as you have a convention between them, and you'll see in C later on when we look at it, and if you look on the web, that you often have different conventions. Like one of the main ones is that you can push the arguments on the stack in reverse order or in forward order, and according to how they're listed in the high-level language. So if you have parameter A, B, C, D in your function definition, then they might get pushed on as D, C, B, A, or they might get pushed on as A, B, C, D. And it doesn't matter which way they get pushed on as long as the function knows how to interpret them. So that's good. So what have we got now? We've got, we can use, let's just put this back, so we'll use our register to pass the value. And the other thing with using registers is that when you have very optimized code, if you access the stack, which is accessing main memory, then it's much slower than accessing registers. So if you only have a few arguments to a function, then you can pass them as registers, and this is often what compilers do when they optimize stuff. So if you only have one or two, like pointers or something that you pass in as arguments to a function, then it could use registers for those. But it's just because we don't have many registers that you often end up using the stack, because you can put on as many arguments as you like with the stack. Right. Let's run this. So we've got X, Y, Z. Right. The other thing is that there's one thing we've got to consider when we're writing functions in assembly like this, and that's that we can have side effects within our functions. Now, just to give you an example, so we've got move ALX print char. Let's just modify our function slightly so that so we're going to print the character. And then let's just, it doesn't matter why we do this, we're just showing what can happen if you start to write more code. Supposing now that we do move AX, what we're going to move into AX, let's just say we move into AX. I don't know, let's put the character that we're not expecting in there, like let's put it something that's bad. Let's put a big B. So let's just assume that B is bad. It'll become clearer why in a minute. So what my function does, it prints a character, then it moves this character B into AX. Remember, B is a single character, AX can take 2 characters, so this will the high byte of the AX will be set to 0. But anyway, I'm just showing you that I'm doing something here. If I run this code now, okay, it prints an XYZ, which is good. So we might think, oh well, our function's fine. We understand how to write functions in assembly. But what we often find is that then we start doing things like this. Supposing we want to print 3 X's to the screen, and we do this, okay. So we move X into AL, which is our parameter, and we're just going to call print char 3 times. And there's no point setting the parameter again because we've already done it here and we don't expect it to change. Now let's just run that and see what happens. Okay, so we don't get 3 X's, we get an X and then a B and a B. And this is happening because there's a side effect of our function. And the problem is that, remember, there are no real functions, there are no real blocks of code, local variables and things like that in assembly. We've got the state of the CPU is all of its registers, and they're not affected by blocks of code, or what we think of as blocks of code. So if we look at what's happening here, we move we move X into AL and we call print char, and it prints the X, which is good. But then inside this print char block of code, it moves B into AX and then it returns. And then when we call the next print char, AX has now got a B stored in it, so AL is going to be B and it's going to print a B out. And the problem with that is that if we're not expecting the function to change, to tamper with the state in that way, then we're going to end up with lots of bugs. And you can see how even with a simple thing like this, you've got a bug. Now imagine if you set off writing code and then suddenly realise that you've got loads of this stuff happening. And the problem is, what we want to do, like we have conventions when we call functions, we should always have expectations about what the function does. And one useful guarantee to give to the function is that when it returns, the state of the CPU is in the same state, all the registers, as it was before we called the function. So in this case, that's what we want. We want to make sure that if we move X into AL and we call print char 3 times, we want them all to print an X. So the problem here is that we're changing the X register in here. Now, what we often see is when we start to use registers inside functions, you often see things like this: push AX, and then before we return, we do pop AX. And all this is doing is it's saying, so the function's saying, I'm going to use the X register internally to do something. For example, here it might do AX and then it might have something else like add AX1, for example. So it's doing some code in there, it's working on AX. But we want to make sure that when we return, a friendly function, a nice kind function, would return things in the same state as it left them. So what it does is, before it uses AX, it pushes the original value that it had before the function was called onto the stack, and then it uses that register to do whatever it needs to do, maybe some calculation where it needs to use that register, and then before it returns, or when it's finished using that AX register, it pops the original value off the stack and back into the X register, and when it returns it should have my X in again, because my X was saved on the stack by the function and then popped off the stack. And so to us it's as though the X was always there, whereas really the X has been in memory and come back again, but the function hides that from us. So as with functions, the whole idea of using functions is to abstract things, to make things easier for us. So if we have some nice convenience, like saying that the functions shouldn't, they should return with the state that they started in, then that's what we want, that's good. And we can start to build up code and have some reassurance about what's going to happen when we run it. So if I run this now, let's see, it should print 3 X's if we've done this properly. Yeah, we've got 3 X's, okay. So although it used that AX register where my X was stored, because it restored it again before it returned, then I'm okay. Now, funnily enough, this when I said function should leave state as it is. Well, that's not always the case. Sometimes if you're optimizing code, especially if you write in assembly parts for C code where you write a bit of assembly, you might have such a good idea about what's happening that you don't want the function to store things onto the stack. As long as you know that it doesn't do that, then you know what to expect. And so sometimes you do, but that's in special cases really. But the other thing is that we don't always want it to leave all the state as it is. Sometimes we want a function to return something, and often when you look at C compiled code by compilers, if I'm not mistaken, then the AX register is used for return values. So when the function's been called, the calling code can look in AX to see what was returned by the function. And if it's a big structure, it can just be pointed to it, so it can still be a single value. But you need a convention about what goes into the function, what comes out, and what the function affects of the outside state when you call it. So there we go. There is another convenient instruction, which is push A, pop A. Let's see what happens now. So it prints 3 X's. So push A and pop A, it just means push all registers, and pop A means pop all registers. So this is, if I wasn't quite sure about which registers I was using and stuff, and I was just being a bit lazy, I could just push all of the registers onto the stack before I do anything, and then pop them all off again before I return. The only problem with things like this is that if I'm only using the AX register here, then there's no reason to store, you know, BX, CX, DX, all the other ones into memory, into the stack, because this is relatively slow. So you need to just think about those things. There you go. If I take them out again, we'll see that it messes up. Now it prints C's because I incremented the B to a C. So that's good. So you've got to be aware of those things. And really what I'm showing you is that functions aren't really functions at all. They're just bits of code somewhere in memory with a label that you jump to and you jump back from them. So you need to make sure when you're creating a function abstraction that it does what you expect it to do. Right. So next, let's try and write a function that prints a string. Let's do something useful, using the ideas from the last lecture. So what do we want to do? Well, let's just, for the time being, let's just get rid of that. Now, I'll leave that function there for now. We're not going to use it. What we're going to do is have another label called print string, and in here we're going to try and figure out what to do. Now, for a start, let's just copy this code here, our BIOS code. We're going to have a return on the end, so let's call ret. Now, we want to print a string, so we need to define a string to print. So the easiest way to do that. Now we could, if we found a string somewhere in memory, and something that might be an interesting thing for you to play around with is to, maybe later on when we've written a few more functions, is to try and write, you could probably write a function that searches memory for a string and then prints it out. So one example is that somewhere in memory there's BIOS loaded, BIOS data and BIOS code. So you could probably quite like that if you look for the string BIOS, like capital B, capital I, capital O, capital S, or even lowercase, and search for that, you would find that string in memory somewhere, and probably near that string you'd find other strings that will print out things that the BIOS program displays. Probably. I mean, I've not tried, but you can imagine that it's all in memory somewhere, so you can find it. Anyway, the easiest way to create a string is to use this db thing, so declare some data. Now let's just try and make our code a bit tidier. So we'll say this is data down here, and I'm going to have a string that says hello, and I'm going to have a string that says goodbye. Good. Now we want to print those out. So, well, how do we print them? First we need to know where they are, so we need some labels. So if I have, let's call this hello message. and we can indent it. I mean, it doesn't make any difference really, but it helps to keep our code a bit easier to read. And we'll have a message goodbye like that. So we've got a hello message and a goodbye message. So if we can print these strings, then it's quite a useful thing to do. And it's, we're learning about functions, we're learning about flow control and stuff like that. So we print strings. So what I want to do is, well, first of all, I need to think about what how I'm going to pass the argument for the string to my function. Now, what I want to do is pass the address of the string, because I don't want to use this label hello message within the function, because it will always print the same message. I want to be able to pass the address, so the offset in memory of that string, the start of that string, the first character, into my function. So I'm going to use a register now called SI, which is just really, it's usually one that's used for representing the source of a string or something in memory. We'll have a play around with it and we'll see that there are some functions that can work on this particular register for optimizing string functions, but we're just going to use it. So this could be any register like AX, BX, whatever, but I'm going to move into there the address of the message I want to print, hello message, and then I'm going to call the function print string. Okay, and now what I need to remember to do is put this. Okay, so here's my first mistake. This jump should be at the end of my code, otherwise the CPU will never get down to my code. So we're going to try and make it so that this prints a message. So I'm using SI for the address of the message, so this should pass the address of hello. Then I'm going to call print string. So what do we need to do to print it? Well, the first thing, it's good to build these things up. The first thing to do is probably to move the first character into AL, just so that we can, we're just going to, if I take SI, now remember, what I want to do here is I don't want to store the address into AL. So SI is going to point to, it's got this label which is actually an address in memory. I don't want to move the address into AL, I want to move the character that's at that address into AL, so I use the square brackets. Okay, let's just check that this works. So it prints an H, that's good. And now what I need to do is make it so that I don't just print the first character, but I want to sort of loop round and print all the next characters. So what I can do is let's have a look what happens if I, well, let's just try this. First of all, it's good to just build things up like this. So if I do add SI, that printed the next character, E, because I added 1 to the address of this hello message. So if hello message was the address of the H, then adding 1 to that address will give me the address of the E, which is good. So we need to do something like this, but we need to loop round and do it. So let's define a loop here. Let's just call it loop. So we need a label. So what we're going to do now is we print the character and then we jump back to the loop. So it's going to print this character and then jump back to the loop. But before we do this, we don't want to print the same character again. We want to increment SI and add SI1. So it will print the next character. Okay. Let's just see what happens. Let me just put some spacing in here to make it easier. We can even indent it a bit more like that, just so that we can see what's going on. So let's see what happens. Oh, What's it doing? Can you see lots of stuff? Okay, what that's doing is there's no way to finish my loop. So so it's working sort of, it's printing H and then it's printing E, then L, then L, then O, but then it's printing the next thing after that, which will be goodbye, and then it will print what's after that, which will be all of this stuff, and then it will just carry on into memory, printing stuff in memory. We don't want to do that, we want it to stop somewhere. Now, the easiest way, and the way that most things work in C, we have null terminated strings. We just have a 0 value on the end, so a byte 0. And if I just, one way to declare that here is to put this on, and I need one on here as well. So, I put that on, let's see what happens now. Ah, the same thing. Well, of course, because it doesn't know about strings and it doesn't know about my null terminators. I've got to write that bit. I've got to make it stop the loop when it gets to a 0. So let's have a look. So it's going to increment it here, and then it's going to go and print the character again. It's going to move the character into here, and then it's going to print it. Now this character, we want to make sure that if it's a 0, we don't print it. We escape that. We escape the loop. So the only way to escape this loop is to jump out of the loop. And so to jump out of the loop, we need somewhere to jump to. So let's call it, in fact, let's indent that there. Let's call it, end. I don't know. It doesn't matter what it's called, but let's call it end. So we want to jump to this label, which will take us out of the loop. So I want to do that if the character in AL is now 0. So if it's got through all the characters, it's got H, E, L, L, O, and then it's got 0. If it's a 0, I want to jump out. So if you remember from the last lecture, we used the comp function. So if I do CMP comp, and what I want to do is compare AL to 0. And then what I want to do is, if AL is equal to 0, I want to jump down to here. If it's not, then I'll carry on and I'll print it. So if I want to jump if it's equal, then I use the JE jump instruction, which just means jump equal, and I jump to my end label. So what does this do now? Let's have a look. Let's just run it and see if it works. Ah, there we've got hello, and it stopped because it found the 0. This is good. Just to show you how that would work, if I take the 0 off the first string here, and we see what happens. It prints hello and goodbye. And the reason it does that is because by declaring these strings like this, this goodbye is directly after my hello. So when it's finished printing this O, the next byte in memory will be this G, and it'll just carry on. If I open that hex editor thing up, where is it? If I do ghex working boot sector.bin, so if I look in here, I'll see that this is my boot sector that my assembler compiled, and I see hello and goodbye just go right next to each other. So as far as my function is concerned, it prints the H, the E, the L, the L, blah, and it just does all of it. Now if I go back and I put the R back on the end, I didn't want to open that, I wanted to run this, and then it prints it. So that's good then. We've got our function now, so we should be able to now. Should be a reusable function that we can use. We could put hello goodbye message. So now we should be able to see hello goodbye. Printing hello goodbye. Now it's as before when it printed the whole thing because there wasn't the 0. It's running both of those now. In fact, if I do them in reverse order, goodbye then hello, you'll see that it's printing them both separately. Goodbye then hello. Okay. So there's our function. Well, there we go. So we've got we've got a function there now. And again, it's all using those things like compare, jump equal. So we've made a loop there. The important thing was that we needed a way to jump out of the loop. So we had to create a label where we wanted to jump to, and we jumped here to just immediately after the last instruction in the loop, and then it would return back from there. Just a few little things. You might have caught me typing it before, but you can. I put add one there, didn't I? Let's try this. That does the same, so that works. So I just replaced the add one function with increment function. So you'll find with the CPU that it's got alternative functions that do equivalent things to other functions. Usually the reason for that is that one function is optimized in some way. So if this is incrementing a value by 1, then it's probably more specific for the hardware. It's probably more optimized for adding something by 1 as opposed to adding it by any number, which you can do when you use the add instruction. There's lots of little things like that, but really if you understand the essence of how to use assembly and how to look up information, then you can work your way around those things. The other thing, if I get the right function here, if I remember, move ALSI, if I do load SB, it's working again now. So what's that doing? Load SB. So, well, I've commented out the increment SI, which moves to the next value in the string that it's pointed to, and I've moved this move SI AL away, and it's still working. So what that means is that this function LODSB, which I assume is load string buffer or something like this, that's doing this same thing. It's looking in the SI register, it's moving the next character into the AL register, and it's incrementing the SI register, so the pointer to the next character into the string, into the next address. And it turns out that this function is optimized for working on strings, for printing strings and stuff like that, and also you can use similar functions for copying strings. And because what happens is people write in higher level languages, and the CPU, where things can be optimized, the CPU designers do try to create functions that are needed to help you. So, and that was also the reason why I used the SI register here as the parameter. I didn't tell you that at the start, but it wasn't important then. But it's just because this particular register, although you can store anything in it and you can use it for anything, there's some CPU functions that can act on this register automatically, like this one that we looked at. So that's good. So we've got a function now. And again, if you tell your friends that you can print a string on the screen, they won't be too impressed. But then if you explain to them that you had no operating system and you were writing it in assembly, then it sounds a bit more impressive. Now, the other thing we can just do is just a little thing, is that we can, if we want to, we can take functions like this and we can put them into include files. So let's call it myfunctions.asm. If I edit this file, so if you find your code getting a bit untidy, you can do something like this. Check if this works. Now all I've got to do is include my functions here. So if I do I've got to remember what I called it now. So it was this, working my functions. Is that right? Oh, we'll see. We'll find out what happens. See if it works. Ah, it works. Yeah. So all I've done is I've used this include thing, which all it does is it just takes the contents of this file and it sticks them into this file before it gets assembled, and it's really just a way of organising your code. and you'll see later on when we start to write more functions that we can reuse, that we'll want to play around with this. We'll want to use include files just to tidy things up. So there we go. So now, yeah, what have we got? Well, we've seen how to write functions, how to cover all functions. We've understood how we return from a function, how this ret instruction, where's it gone? It's in here now. How this ret instruction uses a stack. It pops the next value off the stack and then it jumps to it. And we've also learned that you've got to be careful with functions, because if they modify state in a way that the callee, the person calling them, sorry, the caller, if the callee, the one that's called, modifies the state of the CPU in a way that the caller doesn't expect, then it's very easy to get bugs in there. And some of them might be very subtle, and you might not detect them until quite late on. So we've looked at include files. Yeah, so that's it really. Functions. So like I said, there's no real thing as a function. It's just we just jump to an address, and it's up to us to make sure that we have a convention for calling the functions, and we understand in the same way how to get a return value from a function. And like I said, usually a register is used like AX or something, some convention, so that when the function's been called, we can check to see if a value's been set in the AX register. And then, that might be the pointer to some address in memory that we understand there's some structure that we can use, or it might be a 0 to say there's nothing to look at, something like that. One last thing then, just a bit of an exercise for you to look at, is using print some hex. So we can print strings in memory now, that's good, we can print characters, but it would be useful to be able to print to take an address in memory, like a 16-bit value stored in memory somewhere, to pass the address of that into a function, and that function then prints out the contents of that address. Suddenly, by having that function, it would allow us to inspect any area of memory. And we'll see later on in the next lecture coming up, when we're loading data from the disk, loading more data, like how you would bootstrap an operating system. We need to check that the data's been loaded, and so we need some way of debugging. And we don't have a debugger, we don't have anything like that at this low level. So if we can just print some hex to the screen, then that's going to really help us. So you can have to think about that. But one little, well, some hints really for that. If you're writing a function that prints hex, it would be good to reuse your print string function. For example, when I call print string here, here I could put in fact, what I'll do is I'll just leave that out. So inside my print string function, let me just, for now I'll just put that back. Let's supposing that we define a print hex function like this. So we have print hex. Okay, and what we want to do is when we call print hex, if I just get rid of this code, I want something like this. This is what I would like to happen. This is something for you to think about. If I do move and then say, I don't know, dx, it doesn't matter where, and then that could be some memory address. Let's say some address in memory. It doesn't matter what it is. It could be something like that. That's representing some memory and some address in memory, and I want to then call print hex, and then that will print out the value in hexadecimal. Now, an easy way to do that is to reuse a function. So you could have a template like this. You could have hex template, and we have db ox, and then here we can just put 0, 0, 0, 0, 0, and then a 0 at the end. And when I call print hex, what I want to do is look at that address in memory and print out the the 16-bit value in hex decibels stored out of that memory. So I don't want to print that address out because that's not useful. I want to print what's stored at that address out. But I can use in my print string function, I should be able to use in my print hex function, I should be able to use my print string function, doing something like this. If I do move si hex template, let's see what happens. Okay, so I'm using my print string function again, so I don't need to worry about how to print the characters now, but it's printing that template out. Now my goal to make this work is to then figure out how to edit these bytes in memory. I could calculate the offset, because this, for example, this hex digit, which will be the 4 bits, the highest 4 bits of this hex string here, will be at address hex template 0, 1, 2. It will be the second. It will be, if you add 2 to the hex template label address, you'll be able to get the address of this particular character, and we want to change that to, you know, like an A, B, C, D, E, F, and do the same for the other one. So there'll be some kind of loop in there. Now one thing you'll need to do that is to be able to use, you can look at for the AND instruction, and CPU instruction, which modifies 2 values, and you can look for the shift right function, which you can shift a value so many bits to the right, and using those 2 things you should be able to make something that prints hex. It's just for you to think about, really. I'll come back next time and I'll show you an example of how I did that anyway. But if you can print a hex string to the screen of the value in memory, then that's very useful. We can search for things in memory, we can check whether things have been loaded correctly from the disk, and just with those things it will give us the next step that we can use to build up, to bootstrap our operating system. And we're going to carry on with this stuff and just keep going hopefully until we can load some C code, a C code kernel that we can write for our operating system. So there you go. So have a think about that stuff. Just to recap, yeah, we looked at functions. I told you what a function was. A function doesn't really exist. We looked at how we can call functions and return from them. We considered how we can protect the state from the outside of the function by using, like, pushing registers onto the stack when we're going to use them inside the function, popping them off before we return. And then we looked at include files. We made a function that prints a string, which is really good at this level. It takes a bit of thinking about. I've done this before, so, and even when I come back to do it, I still have to double check whether it looks right and stuff, and check that it compiles. So just take your time with it, really, and try and get familiar with what's going on. And on these things we can build up and up. Any piece of code, all it is just a combination of functions that call each other, and you know, it's just jumps to memory, back from memory, back to there, back to here, and there, and there, and there, and that's all it is. So that's why it's good to look at this low-level stuff, because we can see how it works. That's it, really. So thank you very much, and I'll come back again with some more stuff next time. Okay, thank you. Bye.